So, welcome all. We are today working on parsers. We are starting parsers with the basics of context-free grammar. Understanding how grammars are related to parsers. What is the role of parser, what the type of the parsers it can be, and also how the grammars can be ambiguous, and what are simple procedures for removing those ambiguity. So, it's starting. Let me tell you about parsers. So basically what is being done is these parser will obtain this string of tokens from the lexical analyzer, and it will verify that these strings of token names can be generated by the use of the grammar of the source language or not. So if at all it can be generated, it's okay, it will be passed to it, a parse tree will be created and sent to the next phases of the compilation process. And if at all it is not able to generate, in that case it will show the error that there is some problem, the string was not accepted. So this is something that we have seen. So in parsing process, basically you can understand that we usually use this context-free grammar. Most of the programming languages, they use context-free grammar. And while parsing, what is being done is, given a grammar G and a sentence W, what we do with this sentence, we try to verify whether this sentence is acceptable according to the rule of grammar or not. So sentence W in language of G, we traverse the derivation or parse tree for this sentence W in some standard order. We will see what this standard order can be. So we can use some standard order and traverse it, and then we will try to fit whether it is we can actually derive this W or not. So actually what is this? This tree might be produced explicitly or might not be produced also, but the control flow of the parser corresponds to the traversal. Now this is a simple example. You have seen this grammar earlier also, where we are trying to have a grammar for our program. For a program, it can have a statement or a program statement. Okay, so this statement can be assignment statement, or if a statement assignment statement can be id is equal to expression, or if a statement can be if expression statement expression can be id or int, or expression plus expression. id can be terminals this, int can be terminals this. Except these symbols ABCD or 0 1 2, other all symbols are non-terminals. In between these symbols equal to, semicolon, or these are operators or symbols which are just terminals, I should say. Okay. So now let me understand how this derivation tree can be built for a simple sentence W. Let us have a W which is A is equal to 1 semicolon, and then if a statement if this is expression A plus 1, and if condition is true, then B is equal to 2 semicolon. So a program, for this production you are saying program derives a statement, or program derives program statement. So we are using this production program derives program statement, and then in the next case we are using program derives a statement derives the assignment statement derives this thing, and id is equal to expression semicolon, expression isn't one. So in this way this statement is also derived. So this is how we derive our this thing, strings. If a given string, for a given string, if we are not able to derive it using this parse tree, in that case we will say this string is not acceptable. Okay. Now let me tell you about standard order. So what a standard order can be is usually we use this left to right. Given the string, we read the string from left to right. Other thing is we want to be deterministic. Okay. No backtracking means backtracking is possible, but here we are considering no backtracking. If at all backtracking is possible, it means that we can go in a particular direction in tree, we can come back and try for the next direction. We can come back and try for the other, and in this way we will try all the combinations, which is brute force. So if we are going for brute force, then it is true that we will get a correct result, either it is accepted or not, but it will take more time, you can understand, right? So we are not thinking about backtracking, we want to be deterministic. Okay. Also we want to examine the source program from left to right. So that is we want to parse the program in linear time in the order it appears in the source file. Okay. Now let me tell you about the common orderings. Like it can be top-down parser or bottom-up parser. One more parsing can be universal parsers. Universal parsing method will be actually, some algorithms are there in universal this thing parsing. It can be something like Cook-Younger-Kasami algorithm or yearly algorithms. They can actually parse any grammar. It doesn't matter whether what grammar it is. They can use for a general purpose. They are actually general methods, but the thing is they are not efficient. They are actually inefficient. We cannot use them. We don't use them with production compilers. The other two methods are top-down approach or bottom-up approach, where we, in the top-down approach, we start from the root and try to derive and reach the leaf, right? So we start from the root, we traverse the path in depth first order, and we also use left to right, leftmost derivation, where we read the, I should say we derive the leftmost symbol first. Okay, I will tell you about leftmost and rightmost derivation again. So in this is the thing, and in bottom up approach what will happen, you will start from the leaf and try to build up to the root. Here you will use the reverse of rightmost derivation. Okay. So some of the type of this thing is also shown here. What I am saying is the top-down parsers can be LLK parsers. Actually, I should say that with backtracking, one of the possible techniques are there. With top-down, we start from there and go in different direction, brute force. We are not talking about it. But without backtracking, we actually call them predictive parser. They try to predict, okay, we should go in this direction or the other direction. The one direction they have chosen, okay, we will go with this only. So they are predictive parsers actually. So these predictive parsers can be a recursive descent parser or non-recursive descent parser. So actually this LLK parser is non-recursive descent parser. Here this is something I was writing and what happened, I was telling you that it was there are two types. They are recursive and non-recursive descent parser. So LLK parsers are actually non-recursive descent parsers, where the first L is saying that we read the symbols from left to right, and the second symbol here, L, it means that we are using leftmost derivation. This K means how many number of symbols we read. Generally it is one symbol, or it may be more than one also. Now in bottom-up parsers, actually there are different parsers which can be considered as LR parsers. So these can be LR means the first L is from reading from left, R is this reverse of rightmost, and K is this number of symbols read. So these can be of different types. It can be LR0 parsers, SLR parsers, CLR parsers, or LALR parsers. So you will see these parsers. However, we have to understand that there are certain difficulties related to top-down parser and bottom-up parsers as well. In case of top-down parser, you should understand that you have to choose the correct. You have to predict, I should say, predict the correct path. So choosing the right production is difficult in this case, top-down parser. Similarly, in bottom-up parsers, you will have to identify the correct handles. In this case, when we come from child to root, we call them, since it is the opposite direction, we call them handles. So there are some more things, but you should understand that we are calling it handles. So using these handles, so finding these handles are difficult in this bottom-up parser. Some other useful things I am telling you is while at each node during traversal, what we do is we do some more things, like we can construct some full parse trees, we can construct abstract syntax tree, we construct linear lower level representations, and we can generate a target code also while traversing. So this is usually done in one pass compilers. So there is something called one-pass compiler and multi-pass compiler. Let me tell you here only that these one-pass compiler will compile in just one single pass and generate your code. However, in multi-pass compilers, module-wise it is done, and it actually, you can see if you have front end and back end, it is multi-pass. So it will generate intermediate representation, and then again it will work on it. Multi-pass compiler. Actually, what will happen is since this thing, single pass compilers actually have some advantages also, that it takes less time, but it takes more memory. However, multi-pass compilers take similar or more time, but they take less space, and they are being preferred. Now let me tell you about context-free grammars, which are for tuple this thing, where this n is a finite set of non-terminal symbols, sigma is finite set of terminal symbols, p is a set of productions. Set of productions, you can understand it is something like A derives B. It is like something A derives B So what happens is, these capital letters I am considering, I will tell you the notations in the next slide, but these capital letters, let me tell you, it is non-terminal symbols, and there can be some terminal symbols. So here what I am telling you is, it is n into n union sigma, which means the non-terminal symbols derive the set of terminal and non-terminal symbols. So in right hand side it can be terminal or non-terminal symbols. S is the starting symbol, right? So now let me tell you about some standard notations. I am saying using this side. What is happening is, a small abc will be the elements of sigma, a small w x y z will be elements of sigma star, abc capital they are as non-terminal symbols, x y z will be the union of non-terminal and terminal symbols, alpha beta gamma will be the union along with this lambda epsilon also. If at all we have a derives alpha, or this symbol a double colon, this is also a derives alpha. So this means that they are already present in production P. Okay, so we also call this as production. Now derivation relation, I am telling you about if you have something alpha, non-terminal symbol alpha A and gamma, then this non-terminal symbol A can be replaced by beta if at all there is a production A derives beta in P. Okay, so this alpha and gamma are any combination of terminal and non-terminal symbols. However, this is A which is being derived, right? Other thing is A transitively derives W, which means A can derive to something and that something can derive to some other thing, and last we can get this string W. So we can write directly A as clean, this transitively derives W. So the other thing I can tell you about leftmost derivation and rightmost derivation. Actually, let us say this W is a string of terminal symbols. So since if it is terminal symbol, what is happening here, you can see on the left hand side you have all the terminal symbols, then you have one non-terminal, and later on you have any combination of terminal and non-terminal symbols. In that case, if at all it is leftmost derivation, what we do is we have to understand actually our non-terminal symbol, I should say the first non-terminal symbol from the left. Okay, so here as I can tell you, the W is the all terminal symbols, so the first non-terminal symbol from left is A. So if it is leftmost derivation, this you will have to find the production related to A, which is A derives beta. This is a production in your grammar, so you are replacing A with beta. Okay, this is derivation, and actually you are replacing the leftmost variable, leftmost non-terminal, so it is leftmost derivation. Similarly, if you will derive or replace the rightmost variable or non-terminal, in that case you will call it rightmost derivation. Here you can see all the symbols on the right hand side are already terminals, and then the first symbol, first non-terminal symbol from right is A, so A is being replaced. So we will only be interested in leftmost derivation or rightmost derivation. We are not thinking about both of them, means in one derivation. Then languages, actually for A, in non-terminal A, if you want to say language of this A, it will be the string W. Okay, let me have the pointer. So this W, if you can derive W from A, after derivation, if A can derive W, then this W is part of language of A. So if S is the start symbol for the grammar G, so you can define the language of this grammar G as the language of the start symbol S. Okay, so whatever we can derive from the start symbol, it will be the language of this grammar, no problem. So there is something called reduced grammar. Reduced grammar means we will not have any extra production, any useless production. Okay, so we will have those productions only which are actually being used. We will not keep any production which are useless. So a grammar G is reduced if and only if for every production A derives alpha in G, there is a derivation in which it is being used. Okay. So what we are saying is convention is we will use reduced grammar only. Otherwise, it will be. We will have to make extra steps, extra symbols, extra effort, however, which is not needed. Now let me tell you about something called ambiguity. So a grammar G is unambiguous if and only if every string W in the language of the grammar G has unique leftmost or rightmost derivation. Okay. In fact, I should say a grammar can be ambiguous if they have more than one leftmost derivation or more than one rightmost derivation. Okay. So we actually want unambiguous grammars for parsing. Ambiguous grammars for arithmetic. This is a classic example. Let me tell you about this example. That expression is actually we use plus, minus, into, and divide. So this expression can be expression plus expression, expression minus expression, into, and divide. And in last, this expression can be replaced by int 0, 1, 2, whatever 9. Okay. So now you have to tell me how it can be ambiguous. Okay, I know I have to tell you. So it is ambiguous. How can you show that a particular grammar is ambiguous? For showing this, you will have to try to find two different leftmost derivation for this particular, for any particular string. Given a string of symbols, you will try to find leftmost derivation for it. If you are able to find two leftmost derivation for it, in that case you can say that the grammar is ambiguous. So let us try. Here you can see for this grammar, expression gives expression plus expression, expression minus expression. So one string we are using 2 plus 3 into 4. Okay, we want to derive it using this grammar, whether we can or we cannot. So there are two options. We can go for expression plus expression or expression into expression. If we will go for expression plus expression, then in the next stage this expression will be again derived as expression into expression, and later on we will find 2 plus 3 into 4, right? However, what will happen, the result of this thing will be 3 into 4, which is 12, plus 2, which is 14 answer, right? However, the other option is also there, which will be E. We can use the start symbol first. So E can give you E into E, it is E, and E plus E. In that case you will get 2 plus 3, which is 5, into 4, with the answer will be 20, which is wrong. So you have to understand that you are getting two different parse tree for the same string. Hmm. You are using leftmost derivation in both the cases. Since you are getting these two different parse tree, you can say that the grammar is ambiguous, right? Now here you can see you have used two different operators, plus and into. What if you are using the same two operators, plus and plus? In that case, what will happen? You will use any one of them first, right? What you are going to do is you will have this expression e, and then e will give you e plus e. Now the thing is, with this e you have the option to go for int and derive 5, or you have option to go for expression plus expression and derive 5 plus 6. So in this way, if you are going for e plus e, you will create int 5 and int 6, here also int 7, right? So if you will use it in a different order, you will get this thing, this part later. So I am telling you is this part you can have on this side, right? So if at all this is happening, then you can have two different derivation tree for the same thing, 5 plus 6 plus 7. Now having two different this thing derivation tree means that it is ambiguous. Now you have seen two different examples where in the first case you were having two different operator. Now you are having the same operator, still the problem is there. Now what is happening actually, why this problem is there? Actually you are not able to understand, I should say the grammar is not able to understand the precedence of operators, neither it can understand the associativity between the operators. If it could understand the precedence, in that case it should give the priority to star symbol, right? Giving priority means solving the star first. This is a correct way, correct way means this will give you correct answer, right? Where star is below and plus symbol is at upper layer. So what you can do is you can keep something, the solution here we are suggesting is being suggested, has been suggested I would say, that we will keep different non-terminal symbols at each level of precedence. For each level of precedence we will keep different non-terminal symbols. Then we can isolate the corresponding part of the grammar with this thing, and we will force the parser to recognize higher precedence. Okay. So this is an example. What you are going to do is you will have another symbol term. So this expression is expression plus term now. Now this term is having higher precedence. I should say star and divide. These are having same precedence, so they have been kept at the same level. Plus and minus are at same level because they have same precedence. No problem. So in this way you can see expression, it will be expression plus term, and term will be term into factor or factor, and this factor will be int or in bracket expression, and int will be the terminal symbols. Now let us have this thing with this 2 plus 3 into 4. If you want to have this thing, you will use expression plus terminal, right? No other option. Here you cannot use into symbol because expression is the starting symbol, and from the starting symbol there is no into symbol, right? If at all in some expression there is no plus or minus, in that case you can directly use term symbol, term variable, and e will derive to t, and then from t you can derive whatever you want, right? But then you will not be able to get plus or minus symbols. So you get the plus and minus symbol at the first level, and you write e plus t, and then e can derive t can derive factor can divide int, derive int, and int will be 2. This t will derive the next t into f something, and so on. You will get 3 and 4. Then you can see here that the output what you're going to get here is correct, right? This is having higher precedence, so it will be solved first, and then it is having lower precedence, it will be solved later on. Now what will happen? So now this grammar is unambiguous, is it? So if you derive this thing, you will see what is happening. You can also derive this thing. For deriving this, you will have to use, you will have to come to factor, and from factor you use the expression again. Okay, this is your task. There is something called if ambiguity, means there is if condition. If you remember, if derives, if a statement derives if condition and a statement, or another option is there, if condition a statement else a statement. So there is some ambiguity there which can be solved with the use of different I should say symbols for these two different procedures, where you can keep the if statement with no else separately, and with else clause separately. Okay, so these are the things which are done in this reference grammars. Now there are certain parts or tools you can use which actually automate your parsing methods, which are actually good for specifying operator precedence and associativity. Parser tools actually they also help in showing the productions. Also they can provide this thing facility for longest match. Actually most of them do this, but you have to decide whether you want to use it or not, you know. Means you will have to be careful that if you are aware that what are the things this automatic tool is doing, then it is good, you know. That is the only thing we have seen today. We have seen what parsers are, what parsers are for, and what different ways are there in parsing tree derivation. It can be leftmost or rightmost. It can be top-down approach or bottom-up approach. Different kind of parsers can be there, LLK or LR parsers. We will see these parsers again in next slide. Next video. Thank you.